Okay, hello everyone. Today in this lab session of theoretical computer science, we will take a look at context-free grammars and push non-automated. Let's dive into our slides and see what we have in this session. First of all, we'll take a look at hierarchies of languages and grammars, and then we go to have some exercises on regular languages and recap tests from previous sessions. Then we're gonna have an introduction for a review for context programmers, then push down alternatives, stacks, and exercise tests. Okay, this is a Chomsky hierarchy of grammars. We study regular grammars, and we will jump one step ahead. We will learn context-free grammars, which include regular grammar and itself is part of other grammars. In terms of automated theory, we have finite state machines to accept the regular grammars and languages. So we need to have more powerful automata to accept the context-free machines. Okay, as the recap test from regular languages, we will have which of the following of languages is regular language. The first one is not finite language. It's simply intuitive that we cannot demonstrate it by finite state machine. Okay, we cannot demonstrate this one with finite state machine because first of all, it's not finite. Then it need to keep track of the number of n's in A and C. It kind of need a memory. So we don't have this luxury in finite state machines. So we cannot demonstrate with FS, so it's not a regular language. The second one is not finite, first of all, and then we can have any order of A and B's, and the number of A and B's should be the same. By any order, I mean if it was A, B, B, or A star, B star, so it is regular language because we can show it with finite state. We're gonna loop in one state for A and loop in one state for B. But here the order is not known. We can have A, B, B, A, A. So we cannot show it in finite state machines. After that, we have WWR. It means W and W reverse. First of all, it's not finite. And then we need to keep track of first string to demonstrate to a second string, so it is not possible with FS, so it's not a regular language. The last one is finite. We can have 2 to the power of 1000 nodes. We can show AB to the power of n. Every node can be final and terminating node. So we can finish in every number before 2 to the power of 1000. So it's a regular language. Other recap test is which of these regular expressions are being shown by this finite state machine. S0 is the starting state. So from starting state, we can finish it because it's the finishing state as well. So our regular language should have a star in the end for the whole expression. And from here, we will have A and B together because from A we are going to S1 and it needs to go to the finishing state. So if we get out of S0, we will have A and B, consecutive A and B together. So it's A, B, one time or infinite times, and we have S0 finishing by itself. So it can finish before even going to A. So it's A, B star. The second one is this finite state machine. S0 is starting finishing at the same time. From S0 we can go to left or right. So let's start with left. From left we can have C, D star, C. And if you go to right, we have A, B star, A. And so we can have any combination of C, D star, C, and A, B star, A, any combination. 0 or multiple times. So any combination of A, B star A, C, B star C, multiple times. Answer is B. Okay, let's review the context-free grammars. What is context-free language? Context-free language is a language that can be shown with context-free grammars. In context-free grammars, we can show this grammar with 4 tuples. First one is V, the set of our non-terminal symbols, usually shown with capital letters. T is our terminal letters, usually shown with lowercase. P is our production rules of grammar, so we are generating the grammar with these rules, and S is our starting symbol. Pushdown automatas is an automata using stack mechanism to generate and accept the context-free languages. It's described with 7 tuples, Q states, alphabet, stack, transition, starting, the initial stack top, and the set of accepting states. We will take a look at them. But first of all, we need to familiarize ourselves with stack. What is stack? Stack is a data structure like other data structure, for example, queues, linked list, and it has two main operations, push and pop. Pushing means putting an element into a stack, and popping means taking element out of stack. But how it works? When we push something, intuitively from the name we can guess, we push on the top of each other. So when we want to take, we will take the last element we pushed. So this policy in computer science called FILO or FILO, first in, last out. When you come first, you will go down in the stack and you will serve after all the elements above you serve. So first in, you can see 1 comes first and served after 3, which comes last. This policy is also used in computer memories when you are creating backtracking and recursive algorithms. It is stacking all the function calls and it's taking out of the stack the last function call and go recursively. Okay, let's have our first PDA for this context-free language. We have a language that number of A's and B's should be similar. So what is our strategy? Our strategy can be to push A's into our stack, and when we see every B, for each B, we can pop 1 A from our stack, so we can see if they are equal or not at the end. So it is our transaction from Q0 starting state, when and this is the stack top, and this is the upcoming symbol. When we have A coming and our stack is empty, we will stay in Q0 and we will push the A on top of our stack. So we have ZA in top of our stack. A is coming, we have A in top of our stack, so we push A on top of A. So we want to have all the A's in our stack. And we have A in our stack. After pushing all the stack A's into our stack, suddenly our A's finishes and B is coming. B is coming in Q0 state, and we have A in top of our stack. We said by seeing each B, we will pop 1 A from our stack. So this epsilon means we popped and we don't have anything on top of our stack. Take attention that we are saying we don't have anything on top of our stack, not in the whole stack. Whole stack, the A's are there. We don't have anything in top of our stack. And we go to state Q1 for managing B. In state Q1, we describe this policy for Q0, but it's time for describing it for Q1 as well, because it's a state machine. When it comes, it says I'm not in Q0, so I don't have any rule to operate, and it will terminate. So for Q1, when B is coming, we have A on our stack. We stay in Q1 and we pop the A for corresponding B. Sorry. And in Q1, when we are assuming that the number of A and B are same, So when all B is finishing, nothing is coming, our stack is empty. If this case is not happening, so we cannot accept the language, and PDA says it's not acceptable. This is the diagram of our PDA. In Q0, if A coming, stack empty, ZA, Q0, A coming, stack have A on top, AA. If in Q0, B is coming, and we have A, we pop it, go to Q1. That's what I said. We have to define this rule again for Q1. In Q1, we have the same rule, but from Q1 to Q1, not Q0 to Q1. And if we don't have anything coming, we have the empty stack, we go and terminate our PDA. The next example is this one. We have AN, B2N. It is getting a little bit tricky, so we have double the number of A, B. So what is our strategy can be? Our strategy can be when we are pushing, we can push our all A's into our stack, and by seeing two B's, sorry, we can pop one A. So the numbers will match at the end. Okay, how we can implement this one? In stack Q0, if A is coming and stack is empty, we have ZA, we push the A. If A is coming, we have previous A's, we push the other A on top of them. In stack Q0, if a B is coming and we have A, we go to Q1 and we don't do anything with our A, because we said for the odd number of beads, we don't want to touch our stack. And for even number of beads, we're gonna pop one A. Okay, in stack Q1, when we are in stack Q1, we assume we have seen the bead previously in other stack. So if A on our stack, we pop it. And we go to stack Q2. Q2 is for managing the ignorance of A. So if in Q2 B is coming, we know that we come from state Q1, which we have popped previously, so we ignore it and go to Q1 to pop the other one. Q1 do the same and pop it and go to Q2. This states will go on until we have nothing coming and our stack is empty. So we go to Q3, the final state, and finish our PDA. It will look like this, and these parts are the same as previous one, and the tricky part is here. Q1 is for popping. You can see from Q1 we pop 1A and go to Q2. Q2 for is ignoring and getting back to Q1. And actually this says I popped, you ignore. It says I ignored, you pop. So for every 2B we pop 1A and number will match. Okay, the next question is AN, BM, CN. How are we gonna do that? Actually, we don't care about number of B because B's can come and go, and we don't know how many. We can accept any number, they can come. We don't touch our stack with B. And AN and CN is the same as our first example. Let's take a look. We are stacking the A's here. If B is coming, we don't care. We go to Q1 state with which is for managing the A's, B's, and we keep our stack unchanged. In Q1, if B is coming again, we don't touch our stack. And if the B are finished, C is coming. If we see a C ladder, so we go to Q2 and pop one of our A's because number of A's and C are similar. So instead Q2, if we see any C and we have A in our stack, we pop it until we have nothing is coming and our stack is empty. So you can see it's the same as previous ones. Here we don't do anything. You can see epsilon here because we are not popping, we are just ignoring. And if we see in Q1 C letter and we have A on our stack, we pop it. In Q2 we are finishing all our A's and then we go to our final state. Now let's have a challenge to get familiar with the usage of stack and have it in practice. We're gonna code a PDA to accept this palindrome, even palindrome problem. It's a string that itself contains two parts. First part and second parts are reverse of each other, and the whole string is equal to its reverse. Okay, let's clear this one. Okay, for even palindrome, first we need a stack of characters. We name it a stack, and we need the length of our string. Dot length. Okay, we will go and put until the first part of our stack, a string into a stack. So int I from 0 to I plus I. Sorry. And simply push everything into our stack. Stack dot push input I. Then we need to compare it because stack is giving it into reverse order. So we have W in reverse order. It should match with WR, which is the reverse W. So we are going to, from the second part, half of our string equal to 1, 2 until the end plus I. Another operation of stack, if stack is empty. But empty. It says if our stack is empty, we can terminate because it's not acceptable, or if input I is not equal to stack.top. Another operation which gives the top element in our stack, so we can return false. And if everything is okay, we pop the top element because stack.top just giving the element to us and putting it back. It's not popping it. Stack.top. Okay, if everything goes as in the way we want, we don't get any return false, so we get return true. And that's it. Let's test our code. Okay. ABA is a palindrome, but it's not even palindrome. We wrote our code to match even palindrome. So it should get false. And ABBA is an even palindrome. You can say AB and BA is W reverse. So it should get true. Okay. We saw how we can use stacks in programming. So let's recap our session. We learned about language and grammar hierarchies and where we are. We learned about stack data structure, push-down automators, how to accept context-free language with them, how to draw them. And for the home task from Peter Lee's book, Formal Language and Automators, you will go to chapter 7, push-down automators, and solve problems 4, 5, 6, 9, 10, 11. And for bonus points, you can solve 3 questions, 12, 13, 14. And you will get extra point. And for questions, if you have any question, you can ask right now, or you can contact me via email or Telegram channel after the post. Thank you.